Once you've seen epidote crystals like these, you never forget them. That deep pistachio-to-forest green, the glittering faces, the perfect prismatic rods, and then these little bursts of sparkling quartz shooting out from the matrix. This combination specimen is absolutely incredible. Just look at the dark green epidote blades up to a couple centimeters tall, terminated perfectly, glassy luster, and then these tiny water-clear quartz crystals scattered on what looks like a green velvet carpet. Epidote isn't rare in the Earth's crust, and quartz is literally everywhere, but aesthetic collector-grade epidote specimens like this, they're pretty uncommon. This is the chemical formula for epidote. Iron in the +3 oxidation state, or ferric iron, is what gives epidote its green color. The darker the green, the more iron there is packed into the structure. Pale yellowish epidote has far less iron 3. Epidote was named in 1801 by the French mineralogist René Just Houy. The word epidote comes from the Greek word epidosis, which means addition, and it's a reference to the fact that he noticed one side of the prism base has an additional face. Fine epidote crystals almost always form in metamorphic rocks or in hydrothermal veins cutting through them. Hot, mineral-rich fluids force their way into rock fractures, and that intense pressure cooker environment is exactly what grew these perfect Peruvian towers. The same hot, mineral-rich fluids that form these crystals also drive black smoker vents on the deep seafloor. There, in an otherwise dark and freezing abyss, they create oases of heat and chemistry that support thriving ecosystems far from sunlight. Epidote is a key indicator mineral for these ancient hydrothermal systems. When found on land, they guide geologists to sites where ancient vents may once have existed, and by extension, fossils of the extraordinary deep sea life that once lived around them. And if that weren't interesting enough, rovers on Mars are actively searching for water-altered minerals, which could include epidote, for exactly the same reason. Wherever epidote forms, liquid water and habitable conditions may once have existed. It's a possible clue in humanity's ongoing search for signs of past life beyond Earth. If you'd like to learn more about this, I highly recommend you check out a video called "The Rock That's Helping Us Find the Origin of Life." Now, let's talk a little more about what makes this piece so aesthetically pleasing. For one thing, it has an absolutely spectacular luster. The luster of epidote ranges from vitreous to slightly resinous. Epidote has a monoclinic crystal system, which gives rise to those distinctive slanted asymmetric terminations. The quartz belongs to the trigonal crystal system, exhibiting a classic prismatic habit, tiny, perfect hexagonal prisms that scatter light in every direction. Two totally different personalities on one rock. Both minerals sit right around 6.5 to 7 on the Mohs scale. And yes, the quartz here is classic rock crystal, pure silicon dioxide. It's the same stuff as the sand on beaches and the glass in your windows. The difference is, the atoms are arranged in that perfect lattice structure that allows it to grow these gorgeous crystals. In this specimen, they're tiny, but they catch light in all the right places and give the whole piece that extra little magic. This specimen comes from the San Felipe Mountain in the La Libertad region of Peru. It's not a classic locality most people know like the ones in Austria or Pakistan, but this locality is fresh, modern, and still fairly under the radar. So there you have it, a jaw-dropping combination piece that's beautiful to look at, tells a great geological story, and is a species that might be aiding us in our search for life on Earth, and just maybe, on Mars. I hope you enjoyed this video. I'm Jimmy, and thank you for watching Minerals of Beauty. I'll see you next time.